Today we return to the delights of an RL circuit. Last time it was an RC circuit, and work on our differential equations. So the first thing we do at time 0, we throw the switch to A, which I think we would speak of as charging the inductor. The inductor has no current flowing through it before the switch goes to A, and so there is no magnetic field. So it's not like we're putting a charge on it, but I don't think there's any word like enfielding the inductor. I'm not exactly sure what the right term is, but we power it up. At any rate, we throw it to A at time 0, and then we would do a Kirchhoff loop around this circuit, and you would have the seat of EMF, and then you would have a voltage drop across the resistor and a voltage drop across the inductor, and here is the expression for that back inductance that it's going to push back, resisting the change, resisting that current coming through, and it will and so the EMF is going that way up, and so to go from here to here is to go through a voltage drop. Yes, it reduces the EMF as you go across there. Bingo. Okay, so you recognize this as a differential equation with I as the variable, and so what we need to do is to get the I, all the I's, this I and this I together. So I'll start by taking these two and dividing them into the equation. Now what do? Yeah, I move this over to the other side of the equality, and then I'll divide through by this term. There it is, and then I'll multiply by dt. So it does become this expression, and then I need to now I've got this over that, so I can let u equal this term here, and then du, if you take the derivative of this, would be minus r di, this being a constant. You take the derivative of everything there. You could also do it with characteristic forms that I know it's going to come out. It's a first degree. It's going to come out as e raised to a negative power, and you could figure out what those coefficients a and b are. But I will proceed by doing it by separation of parts, I think is the name for this technique. That I then would integrate both sides of this, and well, it's just kind of crowded, isn't it? I would integrate both sides of this, and here I would get a t, but a constant of integration, and over here I would well, to get this to be du over u, and there's the u, I would need to add a minus r here, so I'm going to have a negative L over R out in front, so that this becomes negative R di. So I would have negative L over R times negative R di, boom, which is what I needed here. And then that's the natural logarithm of u, and then I'll put this value back in for u. So there you are. And then I need to consider that at time 0, the current flowing is going to be 0. this is a useful idea to hold on to, that the back inductance is going to be maximal. When you go from nothing to something, when you first close that switch and current first tries to flow, this says, no, no you don't, no big changes in current, and it gives a back inductance that is so big it is equal to the EMF, and it stops for just that instant. When you first close the switch, the back inductance here is such as to stop all current. So at time 0 there is no current flowing here. If I put a 0 in for t and a 0 in for I, we can see that this constant of integration must be equal to this quantity. But let me return that when you actually work with these kinds of circuits, most typically you'll be saying, what is the current here, or what is the EMF here at time 0? And then the other question would be, what are they after a long time? And after a long time, the current has ceased to be changing, so di dt will go to 0 after a long time, and this will become invisible to the circuit. There will be no voltage drop as you go through here because there is no changing current. And then all the EMF would be dropped across this resistor here. So very nice if they ask you after a long time or right at time 0. It's fairly easy to figure out these and what will be more complex circuits. It is when they ask you at some intermediate time, 1/10 of a second after the switch is closed or 2 minutes after the switch is closed, that you have to do all of this hard work. Okay, so then so I'll raise both sides of this equation, e raised to these powers, and you end up with oh no, I haven't done that. What I did was I multiplied through by negative r over L to get rid of this term, and so there's a negative r over L there. But C is equal to this, and if I multiply that by negative r over L, I just get the natural logarithm of the EMF. Now I will raise both sides as powers of E, and you get E raised to the negative TR over L, and then E raised plus E raised to this, which is the same thing as times E raised to that, and that's E raised to the natural logarithm of EMF is EMF. And then over here you have E raised to this, which is this quantity here. And so then you can put the get the I by itself and divide through by R in the whole equation, and you have this EMF over R here and EMF over R there times. It's good algebra. There's your result. Rather similar to the result you may or may not recall getting for the RC circuit. Let me pull it up here. Boom. Notice that there's a little difference here, that here it was EMF times the capacitance, because that gives you the right dimensions for that Q, and here it's EMF divided by R. That gets you the right dimensions for I, and then this curious term here. And of course, we'll take this R over L, actually negative T over L over R, and we'll take that L over R and we're going to call it the inductive time constant. And again, after this amount of time, then you would have E raised to the negative 1, and so again it's going to be 63% of fully fielded, fully charged here, and then we'll do a discharge, and you would have 30%. You would lose 30% down to 37% of the field. Notice here's the capacitive time constant. Notice this thing that happens, that things end up on the wrong side of the division bar. And it's too bad that it's not L that ends up on the bottom. It doesn't quite work out so pretty, but you're just going to have to memorize those. The inductive and capacitive time constants. And so the expression ends up looking like this when you put in the inductive time constant. And if they were asked you about what happens to the voltage across this as a function of time, you could either do Kirchhoff and take the EMF minus whatever's going on here, which would be R times the current, and there is the expression for the current. And so you could put this in for I, and you could get an expression for V. Or you could take the derivative of this I with respect to time and multiply it by L to get the potential difference across that inductor. And perhaps much to your surprise, either one of these results will yield the same thing as an expression for the voltage as a function of time, which would have appearances somewhat like this. I don't think that they will ever ask you about charge, that in which case you would have to integrate I with respect to time instead of differentiating it. But I don't think that that is ever a request that is made. Now we want to go to the and before I leave that, here's the equation to be memorized, rather like that equation there. We ought to pull it down parallel. Cuse electric was very cute. I don't have anything as cute to say for this one. Worth memorizing, or at least coming close to it, right? You could get the units here right, and then it's 1 minus E. Minus T over tau L. Yeah, who can mess that up? But remember that this result is only from the differential equation for Kirchhoffing around this particular circuit, or one that can be reduced to this circuit. If they had another inductor over here in parallel with this one, or an inductor in parallel with that resistor, or another resistor running here, well, if you had two inductors in parallel, that could be reduced to one equivalent inductor. But if they had another resistor running over here, or another inductor over here, then you would be having to do a new differential equation, and you would get new results. So please be aware that this result we get here is only for R and L in series. Okay, now we want to do discharge. That is, we're going to take the switch and move it to B. And at the moment we move the switch, we're going to have had it at A, and so there will be this I0, this current that was flowing at time 0, and the book pointed out something to me that I'd never realized before, but to actually get this to work, you actually have to make a connection at B before you break the connection at A. It's worthy of thought. I haven't given it much thought, but they say what you need is a make before break switch, which exists evidently. But the current, the I that we're going to be talking about, is the current over in this part of the circuit, which at time 0 will be I0, appropriately enough. But when you throw the switch to B, then immediately this thing here is going to say, whoa, 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 things are changing. That the electric field will start to decay, and because this thing is no longer feeding current into the circuit, and what's going to happen is that this current in green here is going to start to disappear. And so this will say, yo, that's not going to happen, and it will create a a push that keeps the current going. And this is not right, but I have to write it this way. I don't think it's right. We'll check it out in a second, because otherwise the result's not going to come out right. And I don't know how Mr. Houghton is confused, but he evidently is. But let's Kirchhoff around here. And at time 0, you have this current that has been established flowing. So if I Kirchhoff through here, that's going to be a voltage drop. Boom. And then if I go through here, yeah, that's not pushing the current forwards. It is fighting that current. I don't get that, but I'm certain I have to have a negative L di dt here. That this is also a voltage drop. That really doesn't work. How can you have two drops and have it add up to 0? Ah, but here it is, the di dt. The di dt is going to be negative. It's going to be decreasing change in current, so that makes this whole term positive, so it can add up to 0. Yeah, I don't feel real good about that, but let's go on. Alright, then I do this separation of parts. I could also do a characteristic form, but I'll do separation of parts. I'll get all the di and the I together, and all the other terms over on the other side, and then I can integrate, and this time I didn't have to do any substitution. I can integrate that, and that's equal to the natural logarithm of I, and I can integrate that, and that's equal to negative R times t over L, but then there is a constant of integration. And if you're at time 0, if t is equal to 0, then the current should be I0. So C is equal to the natural logarithm of I0, and so I have replaced this with this. Then we have that the raising both sides of this as powers of e, you get an I here, and here you get e raised to the negative t r over L, and then this as an exponent is the same thing as times e raised to that power, and so there's your I naught, and of course I can replace L, this dividing by L over R, by tau L. Okay, so very similar to the results you had for an RC circuit in discharge. I would like you to take that result and graph for me. Suppose we start with throwing the switch to A, and we're doing what I am calling charging or enfielding, and you graph for me what that curve would look like, and then when it reaches wherever it's going, then you can throw the switch to B, and you can graph me the discharge curve right after the charge curve. And if there are any values that you can indicate on this axis, you ought to indicate them. I would also like you to do this graph. Again, I'm feeling uncertain about it. I don't have a simulation to test, but I will by the time you do it. And I would suggest in generating this graph that what you do is think about the fact that the voltage is equal to L di dt. So I would take this graph here and take the derivatives of this graph, that is, look at the slopes, and use that to guide you as you generate this graph over here. I would like to go back to this inductive time constant, which was equal to R over L, and I would like to figure out what the dimensions of that capacitive time constant are. And you can probably remember where this is going, but there on your worksheet, I would like you to do each of these tasks. I would like you to write the units of magnetic field, and that's a good review. Teslas are the units, but you think about the formula that defines magnetic field, and from that you give me the units in terms of newtons and amps, and perhaps some other units. The units of flux, and again, this is a good reminder. What was the equation that defined flux? The units are Webers, but don't give it to me in terms of Webers. Give it to me in newtons and amps. And finally, inductance. What's the formula that defines inductance? Don't give it to me in henries. Newtons and amps. And then take this one, which is in newtons and amps, and you will have used your results up here to help you in this one. I want you to replace Newton meters with joules and amps with coulombs per second, and see what the units of inductance come out to in joules and coulombs in seconds. And then take R, this in the denominator here, and don't give it in ohms, but again, give it in joules, coulombs, and seconds, and then look at that ratio and tell me what the units of the inductive time constant are. Finally, a checkpoint, and this is one, this circuit here is not an RL circuit. Neither is this one. So you cannot use the formulas we have, but you can use the idea that when the switch is first closed, an inductor is going to say, whoa, we don't like change, and it's going to have a back inductance that is so great that no current will flow when the switch is first closed. And then after a long time, there won't be any change in the current, and the inductor will be invisible. It won't have any voltage drop across it at all. So, and you could Kirchhoff around, and the voltage drop would have to happen here and here. So with that kind of reasoning, you can do these three circuits and come up with a ranking when it's just closed and after it's been closed for a long time. Thank you, and I'll see you around.